claims. You also had to do quite a lot of stuff. Essentially, those of you who never organized SAC, I highly recommend for you to do that. This is a wonderful event, and I think that history shows that actually there are quite interesting things published in it, and it's a good contribution to the community. So, without further ado, it's a great pleasure to start the first session of SAC 2020 of the technical session. We had 2 days of summer school. Our first session is on symmetric key, and two things actually. If you have any questions, as you can see, you can all unmute yourself and ask questions. Please use either the Zulip or the chat. We will be monitoring them. Second of all, speakers. I would like to kindly ask you to identify yourself by raising your hand if you're a speaker of the session. And once you finish giving your presentation, make sure that you stop sharing the screen for the other speakers to start speaking. So speakers, please use the Zoom wonderful feature called raise your hand, and raise your hand so I can see who is going to give which talks. Thanks, Sam. Okay, so I guess Sharam is going to present the first paper, right, Sharam? Yeah, you're mute. So
yes.
The first paper, Prince version 2. I think it's the Persian Prince, right? What Prince? Cipher Prince. Okay. More security for almost no overhead. Dusan Bozhilov, Maria Eichelseder, Miroslav Kanezhevich, Baptiste Lambert, Gregor Linder, Thorben Mus, Ventislav Nikov. I'm sorry, it's part of your 5 minutes. Sharam Rasulzada, Yusek Todo, Friedrich Weimer, and Sharam is going to give the presentation. Sharam, the floor is yours for 5 minutes. Start the clock.
One moment.
In the meantime, you see David sending you the link to the Zulip channel. If you have any questions to Sharam or any of the other speakers.
Can you see my screen? Okay. Thank you all for introduction. I'm Shahram, and I'm going to present our work, Prince V2, which is a joint work with the other 9 colleagues that are listed here. Prince is the first publicly known low latency family of block ciphers presented in AsiaCrypt 2012. The ciphertext follows the FX construction. That is, the core cipher is protected by pre and post whitening keys, and these whitening keys are independent of the key for core encryption. Prince has 64-bit block size and 128-bit key size that the key is separated into 2 parts, K0 and K1. K0 is used for whitening keys, and K1 is used for the core encryption. Besides, the Prince core follows the alpha reflection property, which means that decryption with key K1 is the same as the encryption for key K1 plus alpha. This figure shows the encryption for Prince core. It starts with a round, a forward round, and the key addition before. This round is iterated for five rounds, and note that all the round keys are the same, but in the other direction, our inverse is used as backward round, and note that the round constant here in backward rounds are in a way that its difference with the mirror round constant is always alpha, and this is fixed for other backward rounds. And one important point here is that the inverse of all these backward rounds is the same as 5 forward round, but instead of working with key K1, it works with key K1 plus alpha. And to connect this forward round to the backward rounds, designers used one keyless involutive round, the middle round, and this results the alpha reflection property of the Prince core. The round operations and round definitions are given as these equations, and the Prince designers claim that the cipher is secure against an attacker who has 2 to the n data chosen or known data and time computation power of less than 2 to the 126 minus n. Later in 2018, NIST published his minimum requirement for lightweight ciphers that is providing 112-bit security, while the attacker has access to at most 2 to the 50 bytes of chosen data. So we ask ourselves that, can we improve security of Prince with minimum changes to reach the security level of NIST? And the answer is yes. And for this, we only change the key schedule of Prince to a round key iterating one. And also we used another constant value beta in the definition of the round constants for the second half of the round keys. Moreover, we changed the middle round for the Prince V2, that previously it was keyless, but now we changed it to a keyed round operation. Besides, therefore, the structure for Prince V2 is easily achievable by the implementation of Prince. We only need to change the key schedule. Besides, Prince V2 do not follow the alpha reflection anymore, but still it can provide decryption together with encryption just by using this this approach. We use one control signal that we named it DEC, and this decides to choose which keys are used as the round keys, and then we add this this constant value to the second half of the round keys. So if this is the implementation for all of the unrolled implementation of the Prince V2 only for encryption, just by implementing the swap function and adding this constant value to the second half of the round keys, we can provide both encryption and decryption. So we analyzed the security of Prince V2 against these attacks, and we claim that there is no attack that attacker has access to the 2 to the 50 bytes chosen or known, and computational power of 2 to the 112 encryptions. That's all. Thank you for listening.
If you can just unshare your screen.
Yes.
And our next paper, named Non-Misuse Security of the Safe Authenticated Encryption Mode by Elena Andreeva, Amit Singh Bahati, and Damian Vizar. And Amit is going to give the presentation. Amit, the floor is yours.
Yeah. Trying to see how to share. Yeah. Okay. Yeah. So in this presentation, I'll give a quick overview and the implications of our results of the work non-misuse security of the safe authenticated encryption mode. This is a joint work with Elena Andreeva and Damian Vizar. In this work, we investigate provable security of SAF. What is SAF? SAF is one of the two authenticated encryption modes of the fork AE lightweight design, participating in the second round of the NIST lightweight crypto competition. SAF and fork AE were initially introduced in the SAC 2019. SAF is a sequential mode which uses fork cipher as the underlying primitive. Yeah, as the underlying building block. So a fork cipher is a fixed input length to a fixed output length expanding tweakable cipher. And SAF uses the fork cipher in a sequential manner where nonce and associated data is processed in a sequence, and then a message is processed to generate the ciphertext and tag. The left output of these fork ciphers are used to generate the ciphertext, where the right outputs are chained to generate the authentication tag. Since Ceph is sequential and requires a smaller state to be maintained, that is this chaining value, this makes Ceph a more useful target for the most constrained devices. In the original paper, Ceph is shown AE secure against nonce-respecting adversaries. However, in most use cases, nonce reuse presents a realistic attack vector. So the question comes, is Ceph secure beyond nonce-respecting adversaries? And the answer is yes. And in our work, we have shown that Ceph is OAE secure against nonce-reusing adversaries. For our work, we have used edge coefficient technique for the proofs, and surprisingly, Ceph turns out to be OAE secure without any modification in its construction. I'll give a quick overview of what I mean by OAE secure schemes. So OAE security is defined over the concept of online ciphers. An online cipher is said to be indistinguishable from a random online permutation. An online permutation is a length-preserving permutation which preserves the length of a common blockwise prefix. That is, if two messages share some prefix blocks, then the corresponding outputs of the online permutation will also share that many number of blocks. Or in other words, any ciphertext block is dependent on its corresponding message block and all messages processed before it. We target the OAE security definition by Flussman et al. It says an AED scheme is said to be OAE secure if the corresponding ciphertext outputs are indistinguishable from a random online permutation and the tag is indistinguishable from a random string. Now the question is, what does it mean to have an OAE secure scheme? Well, it means two things. First, that if one reuses nonce up to repetition of prefixes, nothing is leaked. Hence, it covers a lot of realistic nonce repetition attacks. These attacks are particularly relevant for the lightweight setting, where nonce can repeat due to various memory or space constraints or due to remote uses. And the second is, OAE also means security against blockwise adversaries, where they may occur. All in all, OAE is relevant for any authenticated encryption scheme, and it gives enhanced security guarantees, but particularly it is more relevant for the lightweight setting because at the cost of only one pass over the data, that is being online, we achieve a level of nonce misuse resistance that none of the NIST lightweight candidates achieved so far to our knowledge. An interesting avenue for future work is investigating the release of unverified plain text, that is the root security of Ceph. Root security is also a natural target in the use cases of lightweight cryptography where similar constraints are applied. We have preliminary evidence showing that Ceph is root secure, and our conjecture is that Ceph is in-root secure without any modification in its construction. With this, I end my presentation. Thank you for your attention.
Thank you very much. If you can please unshare your screen. I remind you all, if you have any questions, please put them in the Zuli channels. David is keep on sending them to everyone. Our next talk is by Samuel Jack and Andre Schroltenholler, a low-gate quantum golden collision finding, and Samuel is going to give the talk. Sam, the floor is yours.
Hi, I'm Sam, and this is joint work with Andre, and our work is about low-gate quantum golden collision finding. So I'll first explain what every part of that title means. So the problem we're looking at is finding golden collisions. We have a random function h, and we're looking for a collision, two inputs that have the same output, but we want a special collision somehow that we would call golden. And this generalizes meet-in-the-middle problems, and so this is one of its main security applications, and in particular we looked at a post-quantum key exchange called SAC. Generally, quantum algorithms for this problem offer less than a quadratic speedup. So previously, and currently, the best classical method is Van Oerschow-Wiener distinguished point finding. And the best quantum algorithms arguably were Ambinus and Tanny, which are these quantum walks that depend on QRAM. So you need exponential amounts of quantum memory, and you need quantum superposition, random access to that memory. And so is this realistic? Can we access that much memory for a cost less than linear in the size of the memory? And lots of people have argued that this is unrealistic, and in fact, it should have a linear cost. And myself and John Skank are among the people who have argued this. And we said, we offer these two more realistic cost models, a G cost where we have bounded arity gates, we can maintain qubits for free, and thus we have a linear cost to access memory. And another one, this depth times width cost, we assume that we continuously pay some cost to correct errors in the qubits. So under these cost models, Ambinus and Tanny's algorithms perform almost the same as Grover with only a polynomial speedup, and all of them parallelize quite badly. So what we looked at in this paper was what can we do under this model? If we're willing to pay a high cost to access memory, can we still do something better than Grover's algorithm? And our answer was yes. And we also looked at, is there a way to parallelize better? Again, assuming these high memory costs. So we used a quantum walk on distinguished points. And so in quantum walks, we found that the optimal was when we balanced the cost of some oracle against the cost to access memory. And since the memory cost is so much higher now, we pushed more cost into the oracle by using distinguished points, very similar to the Van Oerschow-Wiener classical method. So we got this gate count of n to the 6/7. It was the first gate count below n for this problem, and using exponential quantum memory, and in fact, the same time memory trade-off as the previous algorithms. So really what's happening is we have a lot of qubits and they're just idle for a lot of the time. We're really using the fact that we're allowed to keep them idle for free. But supposing maybe we don't want to keep them idle for free, we want to assume that there's extra cost to that, can we do better when we want to parallelize as well? So there is a good parallel method. It's sort of a multi-Grover, and it works well and parallelizes perfectly in a non-local model where qubits can talk to any other qubit. But if they're locally connected, the advantage is not as good. And we found that you could amortize the communication costs by using distinguished points again. And this allowed us to parallelize that method perfectly down to a depth as low as n to the 1/2. And this is on a local grid of qubits. And so we took all this to SAC, and NIST has the security levels for post-quantum cryptography based on symmetric key crypto and its quantum security. And so we also looked at the regular collision problem, which defined levels 2 and 4, came up with a parallel algorithm for quantum collision finding. And then with that, we looked at SAC under these security levels. And we found that the security was lower than the previous estimate under these cost models, but it still meets all the NIST security levels that it claims to meet. So thank you for listening, and I look forward to answering your questions.
If you can please just unshare the screen. So yeah, thanks. Our next paper is Improvements to Quantum Search Techniques for Block Ciphers with Applications to AES by James Davenport and Benjamin Pring. And I suspect Benjamin is going to give the talk. Benjamin, the floor is yours.
Hi, just checking you can see the screen. Great, thank you. So this talk is really about how we can lower the quantum resources required to attack the AES block cipher, and in fact all block ciphers in general. So this is a basic summary of our results. We have the number of quantum gates we require, the depth or time we require, and the number of qubits or amount of quantum hardware we require to mount an attack. As we can see, we can reduce the number of qubits required by about a factor of 1/2 to 1/3. The time required remains static, and we reduce the number of logical quantum operations we require by about 1/2 to 1/3 again. So we can do better with less, essentially, is the message. So to recall, AES is block cipher we have a variable length key. We have a block length of 128 bits. And the goal of the key recovery problem is to recover a fixed and unknown key if all we're given is a set of known plaintext ciphertext pairs. So these are tuples of plaintext and ciphertext pairs, which are related by the fact that the ciphertext is equal to the plaintext encrypted under this fixed and unknown key. Now we can formulate this as a search problem by modeling it as a Boolean function, i.e. this function chi inputs a candidate key, and we simply perform our tests. What does this plaintext encrypt to under the key, and does it match the ciphertext? If all these tests pass, then we say, yes, this is the candidate key. Now the subtlety is that we need to define R, the number of plaintext ciphertext pairs, large enough so that this function chi only has one solution. So here we have the expected number of keys, and so we have 1, which is the candidate key we're looking for, and we have to increase R so that this term essentially is 0. So general terms for general usage of R is 2 for AES 128 and 192, and 3 for AES 256. So we can imagine search being done on a classical computer.
Benjamin, your microphone is muted.
Can you hear me now?
Yes.
Great, thank you. So we can imagine a classical search where we simply test every single key, candidate key on this function chi, and we come up with this classical cost, and Grover's quantum algorithm gives us this quantum cost. So we get a square root reduction in the number of queries. So this is the classical cost, and this is the quantum cost of implementing chi. Equally, we can imagine a classical situation where we simply make a cheap test, where we test, does this key satisfy one plaintext ciphertext pair, and then test chi, the expensive test, if and only if it's passed this cheap test. So we get a classical cost here, and essentially the cost of implementing this expensive test is reduced by an exponential amount. And there exists a quantum analog to this classical search technique known as the search with two oracles method. And what we essentially do is we design an expensive quantum test and a cheap classical test, a cheap quantum test. So generally, the AES circuit with the AES oracle and Grover's algorithm is implemented as a parallel oracle, which has the advantage of being a low depth, but it requires a vast number of qubits, as we simply copy the search space out and perform all these tests in parallel. But we can equally use a serial test, where we simply use flag qubits to test, has this ciphertext plaintext pair been satisfied, and then store this information in flag qubits, uncompute. And we can see that this test requires far more time, far more gates, but requires far fewer qubits. So for a cheap test, we're going to look at what we can do classically. So say we only wanted to test 4 bytes of an AES of a ciphertext. So if we encrypt the plain text under a candidate key and reach the final 3 rounds, and we only want to test these 3 white bytes here, then we can trace back and we can cut out essentially all this computation in gray. And this allows us to save approximately 1.5 rounds of computation and a little bit in depth, and qubits, which can later be repurposed to reduce the depth. So we coded this up in Q#, and we get a reduction in the number of qubits required, and we get a far more expensive oracle, but that cost falls away, and a cheap oracle, which essentially becomes our overhead with regards to Grover's algorithm. We get an advantage in both the metric and depth width metric, as Jacques just discussed. And it's the NIST competition, where we have this max depth constraint on the maximum allowable quantum circuit depth. We only use one plaintext ciphertext pair anyway, with regards to max depth constraints of 2 to the 40 or 2 to the 64 quantum time steps, but we get an advantage in the case of max depth 2 to the 96 operations, because we actually use 2 plaintext ciphertext pairs there. So in summary, it's minor gains, but it's applicable to cryptanalysis of all block ciphers, and AES is 1 bit less secure, at least. Thank you.
Thank you very much. our last talk, and if you can please stop sharing so we can let the next speakers prepare. Unintended Features of APIs, Cryptanalysis of Incremental HMAC by Gal Ben Mocha, Eli Biham, and Stav Perl. I would just remind everyone to post your questions on Zulip, and then we're going to ask all the speakers to answer the questions. And Gal, the floor is yours.
Okay. Hi, everyone. So this talk is about unintended features of APIs, cryptanalysis of incremental HMAC. I am Gal Ben Mocha, and this is a joint work with Eli Biham and Stav Perl. So in this talk, we discuss unintended features of APIs, which are caused by using these APIs differently than what the designer has intended. These unintended uses may result from various reasons, and these features may expose the system to security vulnerabilities and may even be sometimes used to attack the system. So we define a new kind of MAC functions. We call them incremental MACs, which are functions that get a message consisting of fragments and computes an authentication tag for every fragment, where every tag authenticates the entire prefix, meaning the current fragment together with all of its predecessors. And also we require that incremental MAC will also satisfy all of the regular MAC requirements. Notice that in this case, if a certain tag was verified, there is no need to check prior tags. So we identified three different types implementations of HMAC. The first one, the naive implementation, is based on the code in the RFCs, which has first appeared in the MD4 by Ron Rivest and followed later by MD5 and so on. Most existing implementation follow this implementation, and it is used in Siemens ICS protocols products as an incremental MAC. The second implementation, which we call NIPO for naive inner patched outer, tries to protect some of the issues in the naive implementation, and it is the implementation in OpenSSL. And the third implementation, we call it PIPO for patched inner, patched outer, and this is the implementation in Python. Notice that all of the above can be used incrementally as an unintended feature of these APIs. So for the first two implementations, the HMAC security proof does not hold when using them incrementally. And I would like to add that the naive implementation is insecure when using it incrementally, while the NIPO implementation, although it tries to protect some of the issues of the naive implementation, it's actually highly insecure. And the PIPO implementation is better, it is secure. So for the naive implementation, you can see that for some attacks, the time complexity is about the square root of the same attacks against a non-incremental HMAC, against a regular HMAC, meaning that the security is much lower. And for the second implementation, the NIPO implementation, we have a very strong collision attack, which I don't have time to elaborate on, but I want to stress that it is a very strong kind of collision attack. First, because it's independent of the value of the key, meaning that this collision can even be created even before the legitimate party even chose the key. And in addition, this collision also works for every hash primitive that you use. For example, it will work with HMAC SHA-1, HMAC SHA-256, and so on. And it can even be extended to a multi-collision attack, what makes it a key-independent, hash function-independent multi-collision attack, which is the mother of all collision attacks. In addition, I like to add that we also propose the fragment protecting incremental MAC, which protect the message itself, but also the message fragmentation, meaning its division to fragments. And in our paper, we suggest the LA PIPO implementation for length-added PIPO. This implementation is based on the PIPO implementation, and it also protects the fragmentation of the message. We highly suggest that all of the products that use HMAC should be checked to verify whether their code is correct. And we suggest that HMAC libraries should check that their code cannot be used incorrectly. I would like to add that we informed Siemens, and as far as we understand, their latest products are secured. And we also informed OpenSSL, who decided to wait with their decision on whether to update. Thank you for listening.
Thank you very much. Now it is time for all the, sorry, just a second, sorry. Sorry, one of the